I decided, when I was invited by the organizers, I decided to make two presentations. Well, there will be two case studies, and each one of the case studies will represent an intervention which was made by a spin-off of the University of Porto that was created by myself and other four colleagues, which is called NCREP Consultoria e Reputação Edificada de Património. So I will just transmit what the experience we got at the university and the Institute of Construction allowed us to do within this spin-off of the University of Porto. So the first case, it's going to be an intervention on a port wine warehouse in Vila Nova de Gaia, Portugal, on the timber roof. So the timber roof is this one. It's a port wine warehouse which nowadays is being used as an events room. So the owners, which were the first owners, and then they were changed during the process, they changed it to another port wine company. But the owners were the owners from the beginning of the buildings, which were from the 18th century. And they were worried because the structure was quite deformed and unstable. But at least it seemed to be unstable, and as it was an event room, a room that was just hosting 200 people during the weekends mostly, they were worried about the stability of this structure. So one of the things was to know if it was stable or not, if it could be maintained or not, and in case it could not be maintained, they were supporting the construction of a new timber structure, but with the same design, okay, with the same shape. So we started by analyzing the problem, by doing the inspection and diagnosis of courses, following the recommendations of the entities that are concerned with the heritage safeguard. So you see, it's a very long building, something like 75 meters per 15.5 meters. The trusses, which were the main problem, are made of timber, and they have steel rods on the lower line and on the hanger. Okay, so part is steel, but most is timber. This is the drawing that we assessed from the building. You can see that there are lots of trusses. You have all these lines are trusses, and then you have the purlins and the ridge at the top. So this is mainly a cut and the plant of the warehouse. On the top of the warehouse, on the side of the warehouse, you can see that one of the beams was quite deformed. She was not recovered, but the shape was recovered by putting some other pieces of timber on the top of it and embrace them by using steel plates. So this was one of the weak points of the structure, but there were others which were much more important. One of those was that this side structure was pushing the trusses. So the trusses were deformed, as you can see, by this side from the bottom. You can see that there's a double curvature. And then the purlins, I mean the beams that are linking the trusses, they twisted. So they were sub-designed. So the section was not enough. And as you can see here, you have the face of the purlin that was sustaining the rafters, and so it is twisted. You can see it. You could not. Well, normally you should not see it, okay? Because the rafters should be supported directly on this side and not on the corner as we see here. Then another thing is that the common rafters of the trusses were twisted also. As you can see here, we're looking to this side of the truss. So we have the strut, we have the joist, and then we have the common rafter, and you can see that it's twisted. So there was a problem also with the rafters. And then on the link to the walls, there was this strut that was pushing the wall to the outside, and then the joist was not linking, was not being used as a link of the walls. So it was going apart from the wall. So we have something that is pushing the wall, and the joist is not just grabbing the wall. So the wall was rotating to the outside. There was an out of plane movement, as we can see here. So you see that the wall was at this curvature to the outside, and then they tried to sustain this curvature and this out of side movement by putting these steel rods that you can see from the inside, and then the anchors on the outside. So there was, on this particular side of the wall, there was already these anchors that were trying to stabilize the wall. There were a few cracks, nothing special. If we think that this is a masonry wall made of very large blocks of granite, okay, it's a typical masonry from the region of Porto. So nothing special considering that. We did the inspection of the materials. So the materials were in a very good state. With a resistograph, we just measured the relative moisture of the structure. So everything was quite well in terms of state of conservation, but there was in fact a problem here. So we had access to all the documentation of the owner, which was the owner from the 18th century. First, at the beginning, we saw that that was not the original structure, and we knew that because we had square or rectangular sections, and so the rectangular sections appeared at the beginning of the 20th century. So it was not the original one, and it was not because there was a major fire that destroyed the original roof. Then there were other documents that were saying that during the construction of the new one, which was approved by the municipality, there was the collapse of the structure. So even before ending to construct the structure, it collapsed. So we knew that there was already something wrong with this structure from the beginning. This is the plant of the truss that was in the municipality and that we had access. So the thing that finally explained why all this deformation was the explanation for the design that was made first and then implemented afterward. Is that during the design, they didn't take into consideration the compressive forces as something that could instabilize the structure. So all the structure was designed as if all the forces were tensile forces and not compression forces. So there was a dimensioning of the building, which afterwards gave to the structure this unstable behavior and this deformation that we saw on the global structure. So there was a problem from the beginning. It was the structure was under-designed, let's say. So we had this push from that beam that was already deformed, that was pushing the structure to the left, so it was deforming the trusses, and then the trusses and the purlins were under-designed, so they didn't have enough section to sustain the forces that were applied. So that was the problem, and we had this twist of the trusses, and we had this movement to the outside, well, to the side of the trusses, and there's this deformation. So this is the project, and I'm going to just focus in each one of the things that we did in order to maintain the structure and guarantee the safety and guarantee the stability of the construction. So first, we are going to show this bracing system with timber that contained partially this movement and this instability of the whole structure. So as you can see here, this is the design of this bracing system. All the nails or the threads should be on the design, should be there. We cannot just design a project, a timber structure, without just signing all the connections, all the links. This is an example, and as you can see, it was implemented there, and we have these crosses, this bracing system that was the first attempt to stabilize the structure. Then afterwards, we knew also that the purlins that were linking the trusses were under-dimensioned. So what we did was to consider these new alignments in between trusses. So you have one rafter here, another rafter there. So in between the two trusses, we just put these joists, these beams, which are stabilizing the purlins. So we are dividing the span of the purlins into two, and with this we increase it a lot, the capacity of these purlins, and we stabilize the purlins. So the deformation is there, is going to be there, it's not a problem, we just had to stabilize the behavior of these purlins. So the drawings of the design on the left, and then the implementation on the right. So these alignments in between trusses. And then we have another thing, is that the rafters and this strut and even the starting of this joist was, well, the dimension was correct. There were several layers of timber boards, but the problem is that when they implemented it, they did not connect well all the layers of the timber. So this is what the designer proposed, and it was implemented. But as you can see here, we have 1, 2, 3, 4 layers of timber. That was more than enough, but the connection, the link between these layers was not enough. So we had these steel rings embracing the 4 layers, but there was just this rod there just linking them. So the link was not efficient. So we had to just make efficient this link, and we had several not really nails, screws, sorry, screws to just guarantee that they were going to work together. Okay, so we did this for all the other elements that were composed by layers, but that were not properly linked each other. And then we had also that problem of the link between the joist and the wall. So we knew that this is the drawings of the design. So we just designed an L profile that was linking to the joist and then to the wall. So guaranteeing that the joist was going to work as a tie for the walls, was sustaining the walls, was avoiding that push that I told you, the thrust that was pushing this wall to the outside. So we are grabbing the wall, let's say, with this new system, and just guaranteeing that this joist was going to work as the link of the walls. Okay, on each side it was implemented, this system. And then finally we decided that we could also improve the link between the common rafters and the purlins. Okay, so we just implemented, well, at the end it was not this that was implemented. This was a possible system which is commercial, but we implemented a new one, a different one, which is this one, a plate that is twisted at 19 degrees. So we improved the link of the purlins to the rafters, okay, to the common rafters. So at the end, finally, sorry, there was this beam, as you remember, it was quite deformed, and so we implemented a new, and this is a quite new structure. So it's a new element, a contemporary element. We were afraid that the owners didn't like this because it was, well, was running away from the image of the rest of the structure, but they agreed, and so we implemented. This is the drawing of the design. So we use also this truss beam to link the wall. Okay, this is the detail of the link and the detail of some connections. So we have here implemented already. So the link to the wall, it goes to the outside of the wall and has a plate which guarantees this link. Well, some details of the implementation, and then other drawings. Okay, other elements that we use it. Those are commercial also, and then the beam at the end. So it has nothing to do with the other elements, we know that, but we had to have a very stiff element here to guarantee that the trusses were going to be just stabilized and not an element as it was the previous element that was pushing this part of the truss to the left, so just moving all the roof to the left side. So this was the last element, and then finally we had to guarantee, to ensure that all the ties, the metallic ties, were at the tensile stress we wanted. So because we wanted, first, because the ties should be tensioned, and we knew the level of tension that we wanted to implement there, and also because it's the only way to guarantee that the walls are going to be linked one to the other, that is going to work as an element that links walls. So we use the vibration string theory. So we measure the vibration of each one of these strings, of these rods, and we just tune them for the frequency we wanted in order to have the tensile strength that we wanted to put in all those ties. So that was the last part of the intervention. So we could maintain the whole structure by just understanding the problems, the several problems that were on the roof structure, on the timber structure, and then we just implemented solutions for each one of them, but at the end, maintaining everything and guaranteeing that the whole structure was stable. The owner was convinced, but he wanted to be sure. So he asked us to monitor the structure. So during more than 1 year, we monitored the structure by using targets and topographic measurements. So it was a company that did this during a year. We just implemented also some crack meters, and the final result was that, I'm just showing for 1 year, is that we started in one position for the several displacements that we measure on the trusses, and then but also on the walls. We had the starting point at the beginning of the year, or at March, and then the ending point in March. I just signed at this point because when it happened, we thought, so something went wrong. We had a large displacement and there's something wrong with the structure. But please, before trying to understand what happened, please repeat the measurements. And they repeated, and the problem was not the problem with the structure, but it was a problem with the measurement. So I just left that to see that when it happens, we must be worried about that. Of course, we must find an explanation, but before that, just verify that there was something, everything was okay with the measurements, okay? And in this case, it was not a problem with the structure, but a problem with the measurement. So we started at March, and we entered at March of next year with the same displacements. So the structure was stable. We have other results, even with the crack meters, and that was all. We could just maintain everything just by intervening in the weak points of the structure and following the recommendations of course of ICOMOS and other entities that are concerned with the safeguard of heritage. We'd like to thank, of course, the new owner, which is the Floodgate Partnership Wines SCA, and the Construction Institute that at that time also helped us, and the Laboratory of Earthquake and Central Engineer of the field, and Engineer Ricardo Santos of the company that implemented the design in the place. So this was the first example I wanted to show you, and then I'll show the next one, which is another case where we have to intervene to safeguard, okay? We don't intervene just because we want to, or just because it's our desire to change things. We intervene when it is necessary, which was the case on the roof structure that I showed previously. And now it's going to be the same thing with this intervention on the convent of Christ in Tomar. So we had a problem, we're going to see the problem, how we solved the problem, how we attained the final result. So in this case, I should thank, because it was well, I should say that it was the best work I ever saw done by a company in such a sensitive problem that was done by Monumenta. So they were part of this, and they are part of this presentation also. So that's why it's Monumenta there also. So what was the aim of the intervention? we had to ensure the structural stability of the prosecutor's room of the Convent of Christ in Tomar, and of course of the two overlaying elements that were above this room. And the question was made because there was a central column on the prosecutor's office room that had a very high material degradation. And that was one of the main elements that was sustaining the elements that were above. The vaults, we're going to see pictures, the vaults and the walls, okay? The work was commissioned by the Directorate General of Cultural Heritage of Portugal, and the design was made by this design office, which is a spin-off of the University of Porto, and was implemented, the CREP, and was implemented by Monumenta, which was with quite a pleasure to work with them, because when I saw the final result, I didn't want to believe, because it was exactly what we did on the plans. Well, the convent was the headquarters of a religious and military order. Just a very short story about the convent. The Order of the Knights of Templar, and afterwards of the Order of Christ. That's why it's referred to as the Convent of Christ. It's surrounded by the walls of the Castle of Tomar, and it was inscribed on the UNESCO World Heritage List in 1983. Okay, so it was built between the 12th and the 17th century as a main convent. It mixes many different architectural elements, and it contains some of the most expressive testimonies of the history of the Portuguese architecture, like the Romanesque charola, the Manueline church, the window, and the cloister of Dom Joao III. So just three pictures: the charola, the window, and then the stairs, the stone stairs of the cloister of Dom Joao III. So the problem was the very high degradation, material degradation of the central column of this room, of the prosecutor's room of the Convent of Christ, which was located on the ground floor between two cloisters. Well, the convent has at least 4 or 5 cloisters. It's a very large structure. And this high degradation put in danger the stability, not only of that room in particular, but of the overlaying rooms and overlay constructions, okay, which had 2 floors above. So we have what? We have the prosecutor's room. The column is this one in the middle. This is the area of influence of the column. So the area of the weight that was being supported by the column. We see here the floor 0, which is the ground floor, the floor 1, with walls on the arches between the vaults. So we had very large walls just loading the arches between the vaults of floor 0, and then we had on floor 2 we had the cells and the corridor. So with with walls which were much thinner, so not as heavy as the others, and the old roof, the roof of the cells and the ceiling of the cells and the roof of the structure was on timber. Okay, so quite light, but we had all these masonry elements which were quite heavy and were unloading to this column. So pictures. We have the column here. We have we see the large degradation of this column. The column is at the center of the room. We have the ribbed vaults. We have 4 ribbed vaults, okay, which unload on these arches, which by themselves unload on the column and on the walls of the sides. This is floor 1. This is the alignment with the column at the bottom, and we see the walls that we have on the above the arches between vaults, so very large stone walls, and then the last floor with the corridor and the cells and the timber vaults and the roof, the timber roof that was covering all this part. Okay, so we had to evaluate the state of conservation and stability of the whole ensemble, the prosecutor's room and the overlaying constructions, and following, of course, the good practice recommended by the international organizations. And we arrived to the conclusion that, well, the main problem, in fact, was the central column, because there were no cracks and no particular signs on the load-bearing walls of the room itself and of the overlaying rooms. So just a few cracks were detected, and the very well, the heavy part of this problem was on the column and on the material degradation of the column. The shaft of the column was approximately 50 centimeters of diameter and presented, especially close to the base, reductions of diameter up to 15 centimeters. Well, that decrease of the section was increasing the strength, the compressive stress of the column to almost twice the one of the original section, which was estimated to be around 8 megapascal just for the self weight. Okay, so and this was just estimated by the old weight of the elements that were unloading or were within the area of influence of that column. Well, the shaft itself exhibit, and also the basement were the two elements that were, the capital no was okay. The shaft exhibits vertical cracks distributed along the sides. In some cases, they were along the whole height of the shaft, and some of them, there were signs that they were going inside the shaft. Okay, they were not just on the outside, but also on the inside. This type of damage is commonly associated with high levels of permanent stress, a kind of fatigue in relation to the strength of the material, which in this case decreased what and suffered a decrease due to the degradation of the material. So we have a very high stress imposed permanently on that column, and we had the degradation of the material that was decreasing that strength. So it was increasing the problem. The reasons for that degradation were the high level of humidity in the air, which was, we could see this in the degradation of many elements, calcareous elements that were distributed at different heights. It was not just a problem of, because that problem existed on the column, of the water that was rising from the ground by capillarity. That problem existed on the column, but it was not just that problem, okay? We had humidity in around the spaces, and we could see that by the degradation of some architectural elements, stone elements that were distributed in different heights of the, at different heights of the floors. So we see here the shaft, especially at the base. So it was a cylinder, and we have a very large reduction, material degradation and reduction at the base, and at the shaft, at the bottom part of the shaft, with cracks just signing, which some of them are just signed here. So we arrived to the conclusion, after the inspection and diagnosis, that we had to substitute the column. Okay, not only because the degradation was quite high, because we could have a fragile collapse due to these cracks, and also because that was one of the main elements that was supporting the upper rooms. Okay, so we had to substitute to that column. So once this diagnosis was made, it was designed and then implemented an active shoring system, which was adapted to the conditions, and well, that should cause the least possible impact. And I can say that the impact on the structure was, I cannot say zero, but almost zero, apart from the ceramic of the floor that had to be removed in order to protect it, and it was put again afterwards. And that it would allow carrying out the necessary procedures to substitute the column. So the shoring system could not be a barrier to substitute the column afterwards. So this is what we designed. We designed a structure of with 4 diagonals, steel profiles that were linked at not at the capital, but at the the starting of the arches between the vaults, which is this element we're going to see afterwards. And then we have these footings, and the footings were linked by steel rods. Okay, they were linked by steel rods. So we have the weight that was being carried out by the column, and what we did that was post-tensioning these steel rods, and by post-tensioning the steel rods, we were bringing together the four footings at the same time, because they were post-tensioned at the same time with the same level of stress, tensile stress. And so by doing this, we were pushing the diagonals up, and so we were transferring the forces from the column to the four diagonals. Okay, so this was the principle of this system. So you can see here the implementation of the system, okay, with the footings here, which were made of concrete. So the archaeologists were there just doing these excavations in this area. So all the ceramics was removed before. So we have here the actuators, which imposed these tensile forces on the four footings. And then we have the top. Okay, how we did this? We just molded with concrete. We molded these concrete pieces in order to have the best contact with the starting of the arches. So we have the capital here, which was sustained by these two steel frames. And then we had these blocks of concrete that were just ensuring that the force was going to this block in a very perfect contact. Okay. And so we have here the connection between the profiles, the diagonals, and the footings. Okay, and of course here the actuators and the steel bars, the steel rods that were crossing. So the final element there, and then we had the implementation of the system. So we had to monitor everything in order to be sure we knew more or less how much was the tensioning that we had to put at the base, but we had to monitor, of course, to be sure that we had attained the point where all the force were being deviated to the diagonal profiles and from the column to the diagonal profile. So all this was made by STAP and OZ, two companies that were working together with Monumenta, and were monitored by us and by the Director General of Cultural Heritage. So we see here that there's already a detachment. We didn't know if there was a shear key, a metallic shear key in between. We did some tests before, and we arrived to the conclusion that there was not. And so we just put this. Well, you can see here the difference already between the capital and the fust, and the shaft, and then the shaft was with a tear force was moved from the place. Okay, so we're just going a little bit faster. You can see that it's moving, and now at the end it just, well, it's not there anymore. Okay, so it was sandwiched in between these two timber plates. Okay, and it was moved from the place. You can see the shaft, the shaft already here with the base. Okay, and after that we just because the new base and the shaft was already prepared before, and then we put the new base directly at the soil with a film, a waterproof film in between, in order to avoid any other water to rise from the base. And then we have here the base, and we have here the column that is coming into the direction of the position of the previous one. Okay, so we have here already the image of almost final image. Okay, now the final image. Then the blocks were moved from the prosecutor's room out, and all the rest was just treated by together with the archaeology, was just the holes were just how we say this, were just covered with earth, and everything was finished afterwards. We have these films, okay, to protect the original and the new earth that was placed, and then finally the ceramic was placed at the end. So We would like to thank the Direct General of the Cultural Heritage and the Direction of the Convent of Christ, in particular, Engenheiro Júlio Antunes and Architect Luísa Cortesão from the Direct General, and Dr. Rui Ferreira and Dr. Amélia Casanova from the Convent of Christ. And that's all. Thank you. I hope it was not too fast. It was understandable. And afterwards, if there are questions, I'm just available to answer any questions. Thank you.